Hi, welcome to the second semester of calculus. We are going to be starting out with here some finding volumes using integration. And so we're going to have three main methods that we're going to look at here in this particular section. We're going to look at taking an object that has a basic cross section and essentially multiplying it by its length, kind of, sort of. And then methods 2 and 3 are for volumes of what we call revolution, where you take a region and you spin it around a line. And so we'll have what's called the disk method and the washer method, and we'll get to those in just a little bit. But first, we want to look at just what it is that we're doing. For all three of these methods, what we're really doing is we're taking a cross section of the object that we're trying to take a volume, find a volume for, and we're going to stretch it along, in this case, the x-axis. It could be vertical, and we would do something with y, but in this case, we're stretching it horizontally along the x-axis. And so to find a volume for a shape such as this, we're going to do four things. First, we're going to sketch a typical cross section. Okay, we want to know, what does a slice of this thing look like? So if we were to think of it as taking a knife and just cutting it right through there, what is that slice going to look like? In this case, it's probably these weird squiggles on the ends. Step 2, we're going to find a formula for the area of those cross sections. Okay, so we're going to be able, we're going to find areas, and then we're going to establish our limits of integration. Those limits will be, in this case, the x values that my object is stretched out between. And then we're going to integrate to find that volume. And what are we going to integrate? We're going to go back and we're going to integrate that area formula across the x-axis. So let's go ahead and I'll pause the video and I'll set up again, and then we'll look at some examples. All right, so here we are. We're going to be working with this volume here. It's a little hard to see, but we have basically a rectangle that's projected out from the origin along the x-axis. So at the end here, we have a rectangle and its dimensions are 3 and 6. And so our typical cross section is going to be a rectangle. So I brought out the one at the end that had dimensions of 3 and 6. But that's not our typical cross section. Our typical cross section is some other size. But it has to be similar because we do have this projection happening. So because it has to be similar, that means that the width, if it's x, the length is twice that, it's 2x. All of that means that the typical area for one of these cross sections is 2x squared. The 2x for the length times the width. So now, if I want the volume, I just do this all along the x-axis from 0 to 3. Right? I'm starting at the origin, I'm coming out on the x-axis to 3. So I'm just going to integrate from 0 to 3 my function, 2x squared with respect to x. So when I do that, I raise the power to get an x cubed, and I divide the coefficient by that 3. So we get 2/3 x cubed evaluated from 0 to 3. And then as you can see, I plugged in the 3 and the 0. 0 is nice enough to drop out. 3 cubed is 27, so if you clean it up, you end up with a volume of 18. And so there we go. Those are basic cross sections. It works really well with things like rectangles and triangles. We're going to look a little bit more specifically at circles here shortly, but that's kind of the idea. And we're going to extend this out to what we're going to do with the other two methods, with with the disk method first, and then the washer method. Okay, so now we're moving into what are called solids of revolution. Our first option here is going to be what's called the disk method. Basically, picture a frisbee, right? No hole in the middle of a frisbee, just a solid disk. And so first, I want to look at this region. I want to consider the region bounded by y equals negative x plus 1, which I have drawn here, and the x-axis. And we want to look at it between 0 and x equals 0 and x equals 1. So basically, I have this triangular region here that I'm going to try and find a volume for after I rotate it. So the first thing is I have to kind of picture what's happening here. I have a rotation. So this line is going to swing around the x-axis. Okay, and so maybe I should even say that around the x-axis, because it makes a difference where we rotate around. And so if I do that, I'm rotating, so I'm going to get circles. So what we need, or what we have, is that our typical cross section here now is going to be a circle because of the rotation. And so with these solids that are generated by revolution, we're always going to be working with circles. And that's nice because the area for a circle is always pi r squared. Now you notice I used r of x here instead of just an r because our radius is going to be a function of x. So we need to do three things. First, we have to actually find a region, which we did. Okay, we already sketched the region. We looked at where it's rotating. Step two, we have to find the radius. For this particular function, the radius is just the distance from y equals negative x plus 1 to the origin. It's just negative x plus 1. That's the radius. And then the volume will always be the integral from a to b, or in this case from 0 to 1, of pi times that radius squared. So you can see over here, I've worked out this problem. Here's my radius function, or, sorry, that's not my, there, that's my radius. Try that, that's a little better. We don't need the pi yet. My radius is just the negative x plus 1. Okay, that's how far it is from where we're rotating the x-axis up to that curve. It's negative x plus 1. So the volume then, here's my pi in the square, is the integral from 0 to 1, because those are all the x values that encompass my region, of pi times my radius squared with respect to x. Now, I highly recommend just go ahead and pull that pi out. It is a constant. We can always pull constants out of our integration, or constant multiples, I should say, out of our integration. So I pulled out the pi, and then I multiplied out the square. And if you do, you get x squared minus 2x plus 1. That's a much nicer thing to integrate than is the binomial square. So once I did that, then I integrated. I raised my power and divided by the 3, raised the power, and 2 divided by 2 gave me a 1 here. And then the 1 just became my x. And I'm evaluating this from 0 to 1. What's really nice is when you plug in 0, that whole thing drops out. So all we really needed was the 1, which I plugged in. So we had the pi. 1/3 times 1 is just a third. And then minus 1 plus 1 leaves me with pi times a third, or pi over 3. And so there we go. That is your pretty typical disk method. Let's make one that is just a little bit trickier. All right, so let me get that on the board. Okay, so for our next example, it's a little bit more difficult of a region. It's still not terrible, it'll work. I want to rotate the region between y equal to the square root of x and the line y equals 1 around the line y equals 1, and I want to do it between x is 1 and x equal to 1 and x equal to 4. So I started by sketching my square root function in between 1 and 4. If you don't know what a graph looks like, you are certainly welcome to use your calculator, or just start throwing some points in. We know we want to do this from 1 to 4. Plug in 1 to the square root, plug in 4 to the square root, get those values and get a graph. And I want it between that and line y equals 1, which is a horizontal line at 1. So there's my region, and what I'm doing is I'm rotating that around, and you may or may not be able to see it, but I do kind of a dotted curve down here to kind of reflect that over that line, and then I have a circle there to show it. So we're looking at circles, but we need the radius, and that's really where the fun is going to come in. So the radius, the r of x, is the square root of x minus 1. Now, that's a little bit different than what we had before. The difference here is we're not going to the x-axis, which would be x is equal to 0. We're going to this line y equal to 1. And so since we're going there instead, my radius is only the distance from the curve down to that line. And distance is always found by subtracting. And we're looking at the distance here in the y direction because we're going from one curve to the other. So my distance is just subtracting the two things, square root of x minus 1. Once I have the radius, I can set up the volume. The volume is This time I put pi in front of the integral. I brought it out already because it's just a lot nicer. So I have pi times the integral from 1 to 4, because that's where my x values are going, of the square root of x minus 1 squared. If you multiply that out, you get x minus 2 times x to the half. I changed my square root to a half power because that's going to be a lot easier to integrate. Plus 1. I did the integration, so I raised all the powers. Oops, I forgot one though. Let's put that in. There should be a square there. All right, so I raise the power and divide by 2, raise the power. If you divide by 3/2, it's like multiplying by 2/3. That's where you get the 4/3 from, and then the x. And then I plugged in 4 and 1, and if you trust me, it equals 7 pi over 6. If you don't, feel free to work it out. Anyway, yeah, so that was fun. All right, so we have one big thing left to look at, and that's the washer method. So give me just a second, and I will get a new board up. Okay, so I'm going to start this example that will teach us the disk method, or the washer method. I wrote the wrong thing on the board, the washer method. I'm going to start this example, but I won't be able to finish it on this board, so I will continue it on the next screen. All right, so here's what I want to find. I want to find the volume of the solid generated by revolving the region between the y-axis and the curve x equal to 5 over y on the interval from 1 to y between 1 and 10 around the line x equal to -1. All right, so there is a lot of stuff going on here. First things first, let's get the region. Okay, now maybe you don't know what the graph of x equal to 5 over y looks like. You can put it in your calculator, but if you do, you have to solve for y. So in this case, you'd have to multiply both sides by y, divide by x. You'd end up with y is equal to 5 over x. But you have to switch it. The other way to go about doing it would just be to plug in the endpoints for y here, 1 and 10. If you plug in 1 for y, you get 5. Yeah, if you plug in 1 for y, you get 5 for x. And if you plug in 10 for y, you get a half for x. And so we get this kind of curve here. And we want the volume bordered by that and the y-axis. Okay, so you can see I've sketched in the region that I want, but what makes this fun is that now we're going to rotate it around this line here, y equal to, or x equal to -1. And we're going to end up with something that looks kind of like this. And then we're going to make some big circles. But here's the problem. Unlike the last few that we've done, this one has a hole in the middle. If I turn this sideways so we can see it, here's my big circle, and then in the middle there's a hole, which represents this part here in the middle where there isn't any region being rotated. So what we need to do is, this is just an extension of the washer method. With the washer, or keep mixing them up when I say it. With the disk method, we just found the radius and then, use pi r squared and integrate it. Well, now we're going to need an outer radius, which we're going to call capital R of x, and we're going to need an inside radius, which we'll call little r of x. And all we're going to do is that the volume, and you can see I put the pi out front. Okay, it's really easiest just to have the pi out front anyway. We're going to do, the volume is pi times the integral from a to b. In this case, it's going to be from 1 to 10. We'll get to that in just a minute. And then what do we have? What are we integrating? We're just subtracting the 2 radii squared. Okay, so I have the outer radius squared minus the inner radius squared. Basically, pi times the radius squared for the big circle, pi times the radius squared for the small circle, and we're subtracting those two values. All right, so big important thing here, you can't pull the square off of these. You don't want the 2 radii subtracted and then squared. You need to square them both, but first. So for this problem, we have so much fun happening. The inner radius is just 1. That distance is just right here. It's from x equals -1 to x equals 0. That's just the distance of 1. The outer radius, the big R, Well, it's not just the distance to the curve, it's the distance to the curve, that's the 5 over y, plus 1, because we also have to take into account that for that one, for the outer radius, it goes from -1 all the way over to the curve. So that's why I have 5 over y plus 1 for that radius. All right, so then I set up the volume, and so I have pi times integral from 1 to 10 of 5 over y plus 1 squared minus the inner radius squared, which is 1 squared. That part's nice at least. And notice at this time we are integrating with respect to y. So that's different. We've done most of our work with x, but there's no reason why we can't go the other direction. So let me pause it and I will clean up, I'll get rid of some of this and hopefully finish the problem. All right, so back over here on the left side of the screen, I've worked out most of the problem. I haven't quite finished it. I'm going to leave some of it for you. Jump over here so you can see me. So I continued my integration. Basically, I multiplied out the squares. So for the first one, that gave me 25y to the negative second. I think that's 5y to the negative first. 25y to the negative second plus 10y to the negative first plus 1. And then 1 squared is just 1, so that's nice because the 1's drop out. And so what I really ended up integrating here was pi times 1, integral from 1 to 10 of 25y to the negative second. And I wanted to rewrite that as 10 over y because negative first power, if you raise that by 1, you get 0. And that would just make the y drop out. But remember that the integral of 10 over y is 10 times the natural log of y. So that's what I did. For the first one, I raised the power to -1, multiplied the 25 by -1. And so now I have this equation that I'm ready to plug numbers into. We're just going to plug in 10 and 1, and I'll let you go ahead and do that and come up with the answer. So have a wonderful day. Thanks for coming, and hopefully this all works out well for you.